So my talk is focused on GABA, so I'm talking about these J difference editing experiments that Robin just introduced. But almost everything I'm about to say can extend to other edited metabolites with a few sort of modifications. So hopefully it can generalize to designing your general edited experiment. I do have a few quiz questions. Hopefully they work. So I'll just get started. I'm going to fly through these first couple slides just because they're repeating what Robin has just said. GABA is a coupled molecule, and we edit GABA in order to measure it by applying a frequency-selective editing pulse at 1.9 ppm and then observing the coupled signal, or the coupled GABA signal at 3 ppm. And as was said, GABA is measured through a difference experiment. You take the difference between applying this frequency-selective editing pulse from not applying that frequency-selective editing pulse, and in the difference spectrum, you have an observable GABA signal. And in the non-edited signal, or that overlapping creatine, it isn't affected by that editing pulse at all. So in the difference, hopefully, it is completely subtracted. In order to effectively do these experiments, we do acquire a lot of data. We acquire data for a lot amount of time, and I just want to highlight in this different spectrum that I've magnified it by a factor of 5. So it is quite a small signal relative to those creatine signals that we've just subtracted away, and that's going to become relevant in a few minutes. So today I'm going to talk about kind of trying to design these experiments successfully and different factors that you have to think of. I'm not going to go through every factor you have to think of in order to design an effective experiment because that would fill multiple hours, but the topics I am going to focus on are macromolecules, so hopefully you were paying attention a couple minutes ago because you got the answer to my first question, as well as factors like tissue correction or thinking about what tissue is in your voxel, designing your experiment in terms of your voxel size and duration, as well as looking at frequency stabilities and frequency drift. So my first question is, how specific or how sensitive are we to GABA when performing these edited experiments at 3T? And that's how that's going to go. Right. I'll let everybody think about that and maybe get back to my presentation somehow. So, does that move forward? No, that's going backwards. Okay, so maybe this isn't going to work. The answer is, as you just heard, not completely specific. We've got contamination with that signal because and I've sort of exaggerated here, because where we're applying that editing pulse also hits the 1.9 ppm macromolecule signal. And so this effect of co-editing happens, and we've got contamination of our GABA signal by about 50%. What that 50% depends on is how selective your editing pulses are, how stable your scanner is. So, and it also depends on the individual. So that GABA peak is about half GABA and about half macromolecules. So that, again, is why we call it GABA plus. So we've got a couple options. Oh, sorry, I also am new to mice, apparently. Yes, and so I'm highlighting this here again. Our peak at 1.7 ppm is coupled to the peak at 3 ppm, and so we have this contamination of our signal. So we have a few choices in what we do about it. We can accept it. We can accept that our measurement is contaminated with macromolecules. We call it GABA plus, and you will see that extensively in the literature. One of the other options is to try and remove that signal by performing what's called the suppressed GABA acquisition. And so what we typically have this interleaved sequence where we apply that editing pulse, we don't apply that editing pulse, and we take the difference, and that difference gives us our GABA peak at 3 ppm. The other alternative is to apply more specific editing pulses, so an editing pulse of a longer duration, so it's more specific around that 1.9 ppm peak. And then instead of not applying that editing pulse or applying it somewhere else, we apply it symmetric about the peak. So what I'm highlighting here is we're applying our editing pulses in the on condition still at 1.9 ppm, so we're modulating GABA. And in the other condition, the off condition, we're applying an editing pulse at 1.5 ppm, so symmetric about that 1.7 ppm GABA peak. Sorry, 1.7 ppm peak. So in that on and off condition, that peak has been modulated equally. And so I'm just kind of showing the same information here in the same in a different way. In the typical conventional GABA plus sequence, we have our editing pulse at 1.9 ppm. In the off condition, we actually effectively apply it somewhere else that's irrelevant, symmetric about the water peak. But in the suppressed sequence, we apply it symmetric about that 1.7 ppm GABA peak. And so that macromolecule peak sees the same editing in both conditions. So when you subtract it, the effect has been removed. So this, I'm just highlighting what happens when you do this experiment. This data was collected from 12 subjects. We acquired data in both the occipital cortex and the sensory motor cortex, applying both the conventional GABA plus sequence and the suppressed sequence. And what you can see is in that suppressed sequence, you do still have your GABA peak at 3 ppm, but it's much smaller, it's much reduced. And that's because there's not 50% of it being contaminated with macromolecules. So when we look at the relationship between these two things, if we pool all of our data together, we did see a significant correlation between the suppressed GABA measure and the GABA plus. But I just want to highlight some of the limitations of this. It appears to be a regionally specific effect. So we see a significant correlation in the sensory motor cortex, but we don't see a significant correlation in the occipital cortex. And what that means is on an inter-individual level, there's varying levels of that coupled signal. So to say that there's kind of an equal effect of that 50% peak may or may not influence your results. So overall, your GABA plus and your suppressed GABA are significantly correlated, and that is useful because then you can decide whether you need that additional specificity. But we do see there are regional differences in this correlation. And what that means is that there are inter-individual differences of that signal. And this can impact your GABA plus interpretation. So what I'm saying is depending on your individuals and depending on your condition, that may have an effect. Unfortunately, your sequence also has much lower SNR. So the benefits that you gain in specificity are offset by losses in SNR. So there isn't a great solution, I guess, is what my answer is it depends on your experiment. You have to decide whether your losses in signal to noise are outweighed by your benefits in higher specificity, depending on your experiment and depending on your condition. So I wasn't able to think of, and by the looks of it, this might be a good thing, I wasn't able to think of a good quiz question to jump into my next topic, which is looking at tissue correction. So the voxels that we measure for GABA are big. They've got, it's really hard to get a pure white matter or a pure gray matter or a pure, well, you wouldn't want a pure CSF voxel, but our voxels they're mixtures of tissue. And so we have to perform, well, we don't have to, we recommend performing tissue correction to account for those different properties. In typical spectroscopy, we should also be doing this because different tissues, white matter, gray matter, and CSF, all have different T1, T2 properties, and we should correct for that when we're trying to quantify GABA. I'm not going to go into how to correct for the T1, T2 relaxation properties, but I will direct you to the Gasparovich papers from 2006 and 2018, as well as the Gusev paper in 2012, to work out those formulas to move from kind of a relative signal intensity towards more absolute measures, if that's what you choose to do. But what I do want to highlight is there are differences in GABA concentration between white matter and gray matter. We know that there's more GABA in gray matter compared to white matter, so this becomes relevant when you're thinking about your voxel composition and how to interpret your data. I would argue that we perform these spectroscopy experiments to provide information about the metabolites and not about whether you've got more or less gray matter and white matter in a voxel. And this is where tissue correction comes in. So what I wanted to highlight by showing this slide, this was a study in primary progressive aphasia, which is a dementia with more localized atrophy than other neurodegenerative conditions. So I've chosen this slide specifically. Do I have a mouse? No. But we'll look on the left side. There's left-sided atrophy compared to the right side. So particularly in this coronal section at the bottom, you can see on the left side there's more significant atrophy compared to the right side. And so this is going to impact our quantification of GABA. So we want to move away from providing a measurement that depends on that underlying tissue segmentation in your voxel, because we've got better tools, like we can just do a T1 to see atrophy or to see that there's less tissue. What we really are interested in is what's going on with those metabolites, and I would argue that it is different to have a reduced GABA concentration because there is less tissue in your voxel as opposed to less GABA in the tissue that is remaining. And that can have differences of interpretation, as will probably have differences on how you proceed with, say, treatment or modulation of that. So I'm going to belabor this for a couple minutes. So those who understand this, you can tune out for a couple minutes. But what I will argue is that if you've got a voxel that's pure white matter, so the entire voxel fraction is white matter, then your measurement of GABA, or whatever metabolite you're looking at, represents the concentration of that metabolite in white matter. Similarly, if you're looking at a pure gray matter voxel, the fraction is 100% gray matter. The measurement you have represents the GABA concentration in gray matter. And finally, in CSF, if you had a full voxel of CSF, you would measure probably nothing because there isn't any GABA in CSF. However, we have these voxels that are combinations of or are made up of different weightings of white matter, gray matter, and CSF. So our measurement that we get is weighted by those fractions at the bottom. So what do we do about that? Well, one approach is to perform tissue correction and to normalize your measurement by your voxel. So one approach that's used widely with typical spectroscopy or a typical press is to normalize by the total tissue. And this is the correction equation that's shown on the left-hand side. You take your measurement and you normalize it by how much tissue there is in that voxel, or 1 minus the CSF, and you get your corrected measurement. Now that assumes whatever metabolite you're looking at has the same concentration in white matter and gray matter, and we know that isn't true for GABA. We know that there is more GABA in gray matter. So an alternative approach is just to normalize by that fraction of gray matter that's in the voxel. Now that will implicitly assume that there's no GABA in white matter, but we do know that there's GABA in white matter. So depending on your experimental condition, that may become relevant as well. But if we look at those two equations, they're actually quite similar. And they're related by how much GABA you think there is in white matter relative to gray matter. And so we can generalize this to normalize by some weighting on your fraction of white matter. And so that weighting is the ratio of GABA to white matter to gray matter. Sorry, the ratio of GABA concentration in white matter to the concentration in gray matter. So that helps. Now we just have to know what that ratio is. So turning to the literature is sort of helpful in this regard, but it is very variable. From MRS studies, we get an average alpha value of about 0.43. A study that we have performed showed that we got an average over a variety of voxels of about 4.1. So we have an estimate of what that alpha is. And through simulations, we know that it's better to overestimate that alpha rather than underestimate it. So just briefly, this plot on the right-hand side is looking at different alpha values, and because of the way these simulations were set up, you can see at that alpha of 0.5, it doesn't matter how much on your x-axis is your fraction. It doesn't matter what your voxel fraction is, you get the same level of GABA. So for a variety of reasons that I don't want to go into in how these simulations were set up, it's perfect for an alpha of 0.5. Our data suggests that it's about 0.4 to 0.5, and these simulations also show that it's better to overestimate rather than underestimate, so I recommend using this alpha value of 0.5. There are other options in how you can account for these differences between white matter and gray matter. You can do the fraction, just normalize by the fraction of gray matter, that does work, or you can put your voxel fractions as a regressor into your analysis as well, but that is at the expense of power. Okay. I just want to take a couple minutes to show that this does actually matter. This is a study that was done by Eric Borges, in which he was looking at GABA as a function of age. And we know that atrophy happens with aging. This was a healthy population, so we actually don't have any reason to suspect that there's some sort of pathological process going on in which GABA is decreasing. But we know that there is an increase in your voxel fraction of CSF in this voxel because you can't get around the fact that there's atrophy or there is a reduction in tissue. So we see that there is more CSF over time with age in this top plot, but in the bottom plot, depending on what correction you use, you may or may not see a reduction in GABA. So if you don't apply a correction, which is the red line, we see that there is a drastic reduction in GABA with age, but that's just because you have less tissue, which is, as I suggested earlier, is maybe not completely useful. If you wanted to just show that there was less tissue, you could just look at the T1 and see there was less tissue. What is more interesting to me is the fact as to what's going on in that tissue. If you perform the typical CSF correction, you reduce that dependency on voxel fraction, but you still see a significant relationship. Applying this alpha correction that I've proposed, you still see a little bit of a reduction in GABA, but it's not significant. I'm going to skip that for the sake of time and move on to my next question that may or may not work, which is how long should you scan for if you're doing a GABA-edited experiment? Lots of time to think about this. Can you advance the slide? Because it's not advancing for me at all. No? So no buttons are working on my mouse at all now. Okay, but I can't even get to, I can skip the quiz question and just go to the presentation.
Yeah, sure.
So then the next, okay. Yeah.
There's only 4 votes.
There's more than 4 people here.
You've got 3 votes for 11 minutes and 1 vote for 27 minutes.
Okay. So those are actually all correct. I was a little bit sneaky, I guess, and said time versus averages, which are obviously related, but the answer as with all it feels like all of them are, is it depends. It depends on the question you're asking, it depends on how big your voxel is, and it depends on your conditions. So these results here are for a 27 milliliter voxel, so a 3 by 3 by 3 voxel, and what I wanted to highlight was the number of averages that you take does matter. And that seems like a really simple concept, but you will gain stability with acquiring more averages. So on the left-hand side here, where we've got 16 averages, you can see we've got some subtraction artifact in, well, it isn't truly subtraction artifact, but you've got some non-well-modeled signal in your different spectrum. As you move up to 64 averages, you're getting more signal, so you can see that we've got increased GABA concentration relative to creatine. No, you don't. You've got a reduction, actually. But you're seeing a better fit. As you move up to 240 averages, that fit is looking even better, and it's as good as it's going to get in this experiment, at least at 300 averages. So you want to do enough averages in order to acquire a stable result. And so looking at the same data in 5 different voxels, or the same experiments in 5 different voxels, we see that you get a decrease in fit error as a function of averages, and you ideally want to be where you're stable. You ideally want to be acquiring enough data that you're not losing information, or you want to be in the flat part of the curve. So for the occipital voxel, you reach that pretty early, but for your auditory, for this auditory cortex voxel, it actually isn't as stable as quickly. So the answer is it sort of depends on where you are. It also depends on how big your voxel is and what the goals of your experiment are. It's well defined in MR that bigger voxels give you more signal. So if you have a bigger voxel, you can do fewer averages, but that is at the expense of the specificity of your measurement or how specific you are regionally. This is just similar information showing that your stabilization of that GABA to creatine ratio does matter where you are in the brain. So, yeah, well, I just don't know how to, yeah, we'll work on that. So this is alluding back to Dr. DeGraff's presentation about your scanner stability. So if you're designing your experiment, because we work in the MR environment and everybody seems to want to do multiple things, there's very few studies that are just spectroscopy. How would you order these 3 sequences? One being your GABA MRS sequence, one being your DTI sequence, and one being a task-based fMRI. So there are varying arguments as to which order you want to go in. Some people want to get their task out of the way right at the beginning. Some people want lots of time to place their voxel. Some people want to do their spectroscopy right away. Some people want their task at the end. So let's try hand raising. Who votes for number 1? So who would do their task first, I guess? Yeah, you can just go to the next slide. Who would do their spectroscopy first? Okay. And who would make sure they had lots of time to place their voxel? Yeah, so those are fair responses. So there we go. Going to jump into this. We have a problem which is called frequency, well, there's a couple problems with scanner instabilities, but one of them is frequency drift. So where you have these gradient-intensive sequences, such as DTI and fMRI, when you've got these gradients switching on and off, you get some what's called gradient-induced heating in your passive shims. And then you switch to spectroscopy that isn't as gradient intensive, and you have what's called frequency drift. And so what we're showing on the, sorry, I don't know my right from my left, so that's why it takes me so long to say these things. All we have on the left-hand side of the drift is an experiment where you have that gradient-induced frequency drift. This can also happen from just somebody's head drifting, so some motion because people breathe and move. Or we can have similar effects from jumps in your frequency. With this drift, when those metabolites are not so nicely aligned, so all of those 200 averages that you've just collected, when they've started to drift off each other, you see that those peaks become a little bit smaller, they become rounder, and they can become more broadened compared to that aligned condition, and we get this subtraction artifact in the bottom. So what I just wanted to highlight here is that we've got this drift that's occurring over the duration of the experiment, and we can fix some of it. We can apply retrospective frequency correction to bring those all back in line on top. So you've got that NAA and your creatine and choline peaks nicely aligned throughout the duration of your experiment. In truth, we should probably be doing this in all spectroscopy. And so I've got on the left-hand side here an image from Jamie Neer's paper in which he's performing frequency correction on a typical press spectrum to have them nicely aligned. And then I'm just reiterating this drift in the far right. Oh. Thank you. No? That top one. Yeah, I'm new to electronics apparently. So we can correct sort of that gradient-induced frequency drift by realigning those peaks at the end. But we're also applying these frequency-selective editing pulses. So we want that editing pulse at 1.9 ppm to specifically modulate that 1.9 ppm GABA peak here. But if you've got frequency drift occurring throughout the duration of your experiment, where you're applying those editing pulses can move. And so I just wanted to highlight that if you're applying that editing pulse no longer on your GABA resonance, you're not actually editing it anymore. And so what can happen in kind of extreme drift, and so this is on the x-axis is your total frequency drift, and on the y-axis is your normalized signal. If you have no drift, that's great. You've got 100% of your signal. But if your editing pulse offset has drifted too far, you're no longer getting the specific GABA measurement that you wanted, but you're actually starting to edit your MM peak, which is probably not the goal of your experiment. So in terms of your frequency drift, I am sympathetic to wanting to put all of your task at the beginning while your subject is still awake. You have lots of time to place your voxel exactly where it is, but if you've got a magnet that is known for drift, it's really going to affect your GABA edited experiment. It's going to affect your GABA plus edited experiment. If you're doing the MM suppressed experiment, it's going to be even worse. So check your scanner is perhaps the first recommendation, because some scanners don't drift as badly as others. So that's your scanner. The other consideration is your subject. Some subjects just move more than others. Some subjects are going to affect this editing experiment more drastically. So just as some final remarks in terms of designing your experiments, think about the goal of your experiment and what your measurement actually means and what you think is changing. If you're doing a pre-post design and you don't think MM is changing, then maybe you want to just stick with the more basic megapress sequence in which you get that MM contamination, because you can account for it completely. If you're looking at an experiment where you're really worried about your sensitivity and your specificity towards your GABA measurement, you may want to consider whether you should be doing an MM suppressed experiment, for example. Always look at your data. It will help you look at those individual averages, look and see if you've got drift, look and see if you should be removing specific averages or whether you can keep it or not. My other recommendation is to do pilot studies, do repeatability studies on your scanner, and that will help you determine whether you need to be doing or requiring 200 averages, or whether you can get away with a shorter sequence for whatever your goal is, and that will also help you quantify drift. This was a very quick talk. If you would like clarification, please ask questions now or feel free to email me as well. Thank you.